Hi, I am Olivier Alard from the GEMOC and CCFS Center at Macquarie University. And today my presentation is about the use of geochemical information from sulfides and olivine to gain further insight on the mantle lithosphere architecture. Before I start, I personally want to mention the Macquarie Geoanalytical Labs where the magic happened. The CNRS and Geoscience Montpellier, where I hatched some of this idea. And finally, I would like to thank Allscope for supporting our facility. The concept of lithospheric architecture is a key component in the mineral system approach adopted by the industry. It basically acknowledges that the genesis of mineral resources results from cumulative effect of melt-fluid regimes across the mantle lithosphere, which is itself driven by lithosphere scale architecture and composition and favorable transient geodynamic events. These models are built usually using chemical information extracted from key indicator mineral to identify chemical variation across the lithosphere. These data are then integrated to geophysical model to extend this observation laterally. The fourth dimension usually refers to time, which is often the most difficult one to obtain. So my presentation is divided today in two parts. One, dealing with a very rare but ubiquitous mantle phase, the sulfide. Despite their low abundance, they are the major host phase for highly siderophile elements. And at the opposite end of the spectrum, in the second part, I will talk about the major mantle phase, olivine. Very abundant but extremely poor in trace element, and that has, until now, severely impaired its use as a key mineral. I will hopefully convince you that thanks to mass spectrometry advances, olivine is the next best key mineral indicator. So let's now talk about mantle sulfide. Sulfide in the mantle are quite rare, with modal abundances between 0.01 to 0.1% in volume. However, they are ubiquitous. Further, they are usually of small size and are found typically around the 50 micrometer mark, which is not ideal to study them. They have also a low melting temperature relative to silicate, meaning that at typical mantle temperature they are liquid. Further, the occurrence of volatile reduces the crystallization temperature further of the sulfide. Finally, sulfide melts have a low viscosity and low dihedral angle. They can thus percolate the mantle easily. Altogether, this means that sulfide are mobile and extremely reactive in the mantle lithosphere. As sulfide occur either as enclosed in the main forming silicate or as interstitial isolated sulfide, which may form wetland or networks and are also found in reactional patch. These various microstructural positions attest of a different petrogenetic history. These sulfides show different internal microtexture or microstructure which vary between sulfide type, like the enclosed and the interstitial, but also between mantle sample type, like here, for example, in the orogenic massif, or here in the xenoliths from kimberlite. Again, these internal structures are indicative of different petrogenetic history and relate to different crystallization process and composition. Indeed, mantle sulfides show a wide range of composition due to primary magmatic process, but also secondary processes such as serpentinization and weathering. However, what is clear is that both the primary mineralogy and composition of this sulfide change between residual sulfide and interstitial or metasomatic sulfide as shown here. Thus, again, we can use this characteristic to constrain the different petrogenetic history of this distinct sulfide population in terms of sources,
and processes such as melting or metasomatisms. However, they have, unfortunately, a long and complex subsolidus evolution down to about 100 degrees. And they are also often heavily altered by weathering, in this case, or serpentinization in this one, and this effect, unfortunately, obscures the sulfide petrogenesis and need to be seen through. However, whatever the degree of secondary overprint, sulfide are clearly the main host of highly siderophile and chalcophile elements, as can be seen in this figure where the budget of sulfide are shown in red and orange. The very interesting aspect here is that different types of sulfide have different trace element pattern. For instance, enclosed sulfide here have high iridium content and low palladium content, yielding therefore a low palladium-iridium ratio, supporting the nature of melting residue. While interstitial sulfide have a high palladium-iridium ratio, which is entirely consistent with their metasomatic origin. And this fractionation and variability occur in all the mantle sample type, as can be seen here on this slide. Within the HSC groups, two elements are of particular interest: rhenium and osmium. Rhenium behave like palladium. 187 rhenium decay into 187 osmium with a half-life of roughly 42 gigayears. However, osmium behave like iridium, thus large rhenium-osmium fractionation occur within and between sulfide type. This is excellent for dating, as each sulfide evolves with time towards very distinctive 187-188 osmium ratio. Because of that, and the extreme compatibility of osmium and the very low osmium diffusivity of osmium in silicate, silicate shielded sulfide yield all ages corresponding to melting events, while in contrast, interstitial metasomatic sulfide show radiogenic osmium isotopic composition. We thus have the ability to obtain ages directly related to mantle. This is crucial to establish how the lithosphere architecture evolved through time. Remember the fourth dimensions. Indeed, most of the isotopic systems such as samarium, neodymium, or rubidium strontium have blocking temperature lower than the ambient mantle temperature. Further, the systems are based on lithophile elements, which are thus strongly affected by metasomatic event. If we add the fact that crustal rock are more readily accessible, then you realize that most of our knowledge and understanding of the timing of the Earth process rely almost solely on crustal rocks, which is a severe bias. Now, thanks to the rhenium-osmium system properties, combined with the different petrogenetic history of sulfide and our ability to measure this isotopic system in situ, we can unfold the timing of mantle events, such as melting events, but also such as metasomatic episodes directly.
Indeed, now, as done for zircon, it is possible to construct a mantle age sequence using sulfide and to recognize difference or similitude between the different age pattern that you may obtain for each of these sections. But also, you can pick up the various metasomatic source here that you record in your sulfide populations. However, given the small size of sulfide and the destructive nature of laser ablation, it is very rare that you are able to capture both the geochronological information and the geochemical information from the trace elements in sulfides. Therefore, geochemists are always faced with the Cornelian dilemma, choosing between geochemistry or geochronology.
Recently, we have overcome this major hurdle by developing a laser ablation split system, allowing to measure simultaneously rhenium-osmium isotope on the multi-collector ICP-MS, while the quad ICP-MS is recording the siderophile and chalcophile abundances of the ablated sulfide. This method is not trivial, and it takes skill and quite a bit of time. Given the circumstances in the last 2 years or so, we have not been able to jump back on this horse, but hopefully in the next month, we should be able to resume and provide the community with more integrated geochemical data, allowing to both date and geochemically characterize sulfides. Let's now move to olivine. Olivine is the main phase in the mantle, and as such, it controls the rheology and physical property of the mantle lithosphere. Thus, a geophysicist mantle is an olivine mantle. However, olivine is extremely poor in incompatible elements, which are thus too low to be measured. Therefore, geochemists focus on pyroxenes and garnet, which are much richer in those elements. The geochemist mantle is a clinopyroxene mantle. Thus, most of the time, we are not talking about the same mantles. For instance, magnesium number of olivine has already been used as a key indicator in chemical tomography to decipher between a fertile and refractory section. And now we can extract much more information than that. First, olivine is a very widespread mineral, which can be found in mantle xenoliths, but it's also a common xenocrust in basaltic lava, which are devoid of peridotite xenoliths. For instance, in the newer volcanic province or playground, we have numerous xenoliths locality, but we have 10 times more volcanoes which are devoid of xenoliths but contain olivine xenocrust. Therefore, the use of olivine, and particularly xenocrust, will increase significantly our sampling resolution of the sub-continental lithospheric mantle. Further, recently, olivine thermometry has improved considerably this last decade or so. We can now determine equilibrium temperature using aluminium or chromium in olivine, and then obtain pressure relative to the regional geotherm, or alternatively using calcium as a barometer. As you can see here, the correspondence between the classic 2-pyroxene thermometer and the content of aluminium or of calcium in olivine is quite good, and so is the fit between olivine and pyroxene temperature. So, what are we missing to use olivine as a powerful key mineral indicator? What we are missing is to be able to measure routinely ppb level of trace elements in olivine. This is what olivine trace element was looking like 10 years ago. Spiky and very messy. It's due mainly to oxide and polyatomic interferences, but also low counts and high detection limits. This is what we now achieve in our lab: smooth and complete trace element pattern and detection limit at least 2 orders of magnitude lower. We are therefore now able to measure trace elements at the ppb or infra ppb level in olivine in a routinely fashion. We can even now investigate the abundance of siderophile and chalcophile elements at the infra ppb level in olivine. I thank you for your attention, and I hope that I was able to convince you that both sulfide and olivine are key indicator minerals. Sulfide offer a different perspective on the evolution of the subcontinental lithospheric mantle, and they provide badly needed geochronological information and also key constraints on the transport of metal across the lithospheres. The second, olivine, is still in its infancy, but show tremendous indicator potential and a way to bridge the gap
between geophysics and geochemistry. I am looking forward to answer your question in the dedicated session. See you then.